I'd like to introduce our speaker tonight, Richard Nolthenius. Rick, to his Cabrillo College students, has been an active amateur astronomer for 50 years. He got his BS honors in mathematics from the University of Arizona in 1975, Masters of Aerospace Engineering from the same university in 1976, worked as a thermodynamics analyst and designer for General Dynamics Convair Space Division in San Diego, returned to earn a PhD in astrophysics at Stanford and finishing at UCLA in 1984, a postdoctoral fellowship at Stewart Observatory, and eventually decided to settle in Santa Cruz, where he pursued astronomy research at UC Santa Cruz as a visiting researcher and lecturer by holding the Department of Astronomy chair position at neighboring Cabrillo College. In the past 4 years, he's added a position at the New Earth Futures Institute at UC Santa Cruz under longtime collaborator and co-author Sandra Faber. His research interests have ranged widely from chaos theory applied to bar galaxies, application of new techniques of smooth particle hydrodynamics to black hole tidal fields, using planetary nebula as dynamical probes to map galaxy rotation curves, galaxy clustering is a diagnostic of the nature of dark matter with Joel Primack, and during the last decade, the thermodynamics of civilization and its application prospects to our climate future. During these many years, he's long been an active observer, first of lunar occultations, and then on to asteroid occultations, which we'll hear more about this evening.
Absolutely.
In 2024, he observed, reduced, and submitted his data on 91 successful asteroid occultations and 34 so far in 2025. You've been busy.
Yeah, it saves my psyche from actually paying attention to the world, I think.
Rich has been author or contributing co-author on dozens of papers written on these efforts. Richard, I'm going to turn it over to you.
Thank you. That was a very nice introduction. So yeah, asteroid occultations. Every chance I get, it seems if there's one that's somewhere nearby and I'm having a tough day, it's like, Kirk, be at my place at 8 o'clock. Let's go grab this one. So I hope you might enjoy what we're going to do here. Okay, I do have about 80 slides, so I will try to get through all of them. Now there's a lot of science involved, and that's why, well, that's a big reason why I get a lot of satisfaction. It isn't just seeing something cool out there, it's actually contributing to a database. This is actually the most effective way that we have of specifying the orbits of asteroids. And the reason is, there's two reasons. First of all, asteroids move really slowly. And we can slice time up to tiny, tiny little pieces and stamp them onto each frame of high-speed video. And that translates into extremely good astrometry. So if you have good astrometry, that's the measurement of the position of things in the sky, then of course you can do very accurate orbits out to more significant digits. In some cases of the events that I've observed, that actually has application to defending the Earth. There is actually the Earth Defense group that is dedicated to monitoring near-Earth asteroids, among other things, and finding how their orbits change is vital to being able to accurately predict when they're going to hit us, if they will. So that's the science. As I point out here, even the monster telescopes can only see asteroids as little teeny pinpoints. So you can do much better if you've got even just two observers. So here's two tracks across the sky. Myself and Kirk Bender, who actually is here with me tonight as well. Captain Kirk, as we call him. And that's our two tracks there. And you can see how well we've been able to specify this pear-shaped asteroid. The little illuminated sides that you see were determined from a whole different technique, which is very carefully measuring the brightness of asteroids over time and then doing a whole complex deconvolution and trying to figure out what must be the shape of the asteroid, assuming the albedo, the reflected is the same everywhere. Unfortunately, that technique has a lot of so-called degeneracies. I don't mean that in a moral sense. I mean it in a mathematical sense. It means that there's a bunch of different solutions that fit the photometry. And in that case, getting an asteroid occultation can actually reduce and even eliminate that. In this case, Kirk and I were all that was needed to specify not just the shape of this, but the orientation of it. So they already had a decent shape from photometry, semi-decent. This is a reasonably well-known asteroid, but we didn't know exactly where it was in terms of that rotation. The other cool thing about this event, the reason I decided to put this one up, is because Kirk and I were actually on a trip to the White Mountains, and the goal there, the primary goal, was to help a very sick friend of mine who's been doing an ongoing, he's a biologist, ongoing research into monitoring the growth of the bristlecone pines as climate change continues. And he was not able to go up the last couple of years, and so Kirk and I went up last year to gather the data. But, of course, whenever I'm going somewhere, I'll find, gee, I wonder if there's an asteroid path somewhere near here. And sure enough, there was, and so we got it as a nice success. So the Gaia mission, which is this satellite that's up there and has been photographing the sky over and over and over from above the atmosphere and getting extremely precise positions of the stars. And the stars only follow a very calculatable motion in terms of the reflection of the Earth's orbit around the sun, but then also a very linear proper motion as they orbit the galaxy. And so the photography from Gaia has enabled us to get extremely precise positions of stars, especially faint stars. So this is a little bit interesting. The bright stars are the ones that we don't have such great positions on because they're so darn bright they burn out too many pixels. But the faint stars, which is most stars, and most of what these events end up being, these asteroid occultations, are the ones we have really good positions. And if we have really good positions of the stars, and then we monitor the occultations, then boom, we've got the asteroid nailed. So this thing has a shape to it, which we confirm very well with this set of occultations. You can see Kirk and I also participated in this, as did Kent Osaki. Is he a member of your club here? Some of you might know Kent. He lives around here. Ted Swift and Yangtze Liu, also new asteroid observer nearby here. And we got great data. So this is not only important for just monitoring all asteroids in their orbits, but also there are special ones where the NASA people will call up and say, we really need somebody to get the position of this asteroid really, really well, because we've got a space mission on its way to it. So in particular, I'm going to show you, well, several that we have, Kirk and I and some of my other team have helped in doing that. You never know also when you might get a new moon, discover a moon around an asteroid. And if you have a moon, then you can apply Kepler's third law, and that'll tell you the masses. And if you got the masses and you got the sizes, well, now you got the density of the two asteroids. That's something you're not going to get by looking through a telescope. And that allows you to now figure out what is it made of. Is it rich in ice, in which case it'll have a low density, a very high density, maybe it's made of metal, maybe it's made of lightweight rock, and etc. So finding asteroids that have moons, which is pretty uncommon, but there are now a few hundred known, and there's now even a very few that have been discovered that way by occultation, including my work and Kirk's. So I'm going to show you some examples. And this is the level of equipment that you need to do really good work. So this is a Celestron 8SE telescope. There's a toolbox you can buy at Home Depot for cheap. And on the top there's an old camcorder, which you can probably get on eBay now for $100. Mini DV tape, a little monitor you can get for $35. And underneath that is a battery and a video time inserter. So that's a little more expensive. But what that will do is it will take the GPS signals from the satellites and it'll stamp on every frame the time right down to a fraction of a second, very tiny fraction of a second. That's what's key to being able to get the really good events. Okay, so the first event I want to talk about is Phaeton. Phaeton is actually the parent object of the Geminid meteor shower. So how many of you know about the Geminid meteor shower? Hopefully just about everybody, yeah. It's the strongest meteor shower of the year, December 13th. Now this thing has been shedding rocks and probably has a little bit of ice still left in it. And because of that, there's non-gravitational motions involved. And that means you got to keep track of it, otherwise it could wander away from where you think it is. And of course, the Geminids intercept the Earth, and that means this thing is on a path that someday is going to hit the Earth. So if you want to save the Earth, I mean, that's kind of our business, Kirk and I, we're how to save the Earth, then you better keep track of it. So turns out there was a very bright star for these sort of things, 7th magnitude, that's really bright. And it crossed California and Arizona, and this is a super high priority event. There's a mission called the Destiny mission that's on its way to Phaeton. And check it out up close. And we got 60 tracks here laid out. All of these lines here are tracks. And what we wanted was to get 60 people on those tracks, and then we could map out where the asteroid was. We didn't know exactly where. That's why that's a very big, frankly, we knew most of these tracks were going to get misses. Kirk and I joined the effort, and we did not go to the Central Valley where a lot of people went, because we said, why do we want to go there? We want to go to Carrizo Plain. Believe me, this place is perfect for asteroid events. There's a bunch of roads, dirt roads they laid out, thinking they were going to make a housing thing out of this long ago, and of course they gave up on that. But that means all those roads are perfect for laying out observers. Perfect. So this is our spot here for Kurt. That's my tent, and there's his gear, and there's cameras, and this is right after dawn, after a successful observation. And I was assigned a very high probability track. The JPL orbit was deemed to be probably the most accurate, and David Dunham put me on that track. Kirk was nearby, but he got a miss. Not his fault. We knew most people were going to get a miss, but I got lucky. And so there's my occultation. So here's the brightness of the star going up and down, in part because of just random noise. But then there's the occultation down to 0. And the whole thing happened in just 0.24 seconds. So the whole moment of joy was 0.24 seconds long. But that's okay, because it was great to get it. And I'll have you listen to my tape. I got a short 24-second YouTube that'll show that. But we were able to cut the time down to 1/60th of a second because the star was so bright, and still get a very sharp drop to 0. So this whole duration here is only 0.24 seconds before it came back up. And then the green dots is sky. So that's blank sky. So there's what we got, and there's now the outline of the asteroid. And you can see my track there is right in the middle, and there's other tracks here. There's Kirk's, and so we got 1, 2, 3, 4, 5 people out of 60 got the event. But now that we have gotten this, we're now able to calculate the orbit so much better that on future events, we'll be able to concentrate people where they're going to get good data. We won't have to be so wasteful of observers. Now, I'm not going to play that 28-minute video, but I will show where I was. So this is kind of cool. This is my site at the solar farm down there in Carrizo Plain, and there's the Milky Way, and it was, it was great. So late summer night, it was a perfect way to spend a night. Combining our occultation data with data from this doesn't look like damn it data. This is well, anyway, this is other information. Oh, this is from the Arecibo radio telescope. So this object does come close to Earth, as I was saying. And when it's close enough, then the Arecibo radio receiver can bounce radar beams off it. And if you analyze the reflection of those radar beams, you can actually reconstruct an image of the asteroid. And so we did have that, but of course it's only good at the very few times that it comes close enough to do that. And of course the Arecibo radio telescope is dead now, ruined by a hurricane. But through that we were able to also specify where the axis of the orbit is, of the rotation rather. And so now we know this thing pretty well. However, it still wanders a little bit. I'll tell you now, Kirk and I went after the same object about a year ago, and we had a miss. So, anyway. Okay, this is our next event. This is Pluto. So Pluto passed in front of a 15th magnitude star back in 2019, August 15th. The northern limit, predicted northern limit, was up here in Marin County, and that actually makes this area perfect because we get nice, long, extended passage of the star through the atmosphere of Pluto, as well as getting when it hits Pluto and then comes out the other side. So we were really perfectly placed for this. And because we were so perfect, I went and I begged for time on the Fremont Peak 30-inch telescope. And luckily a former student is like one of the honchos there, and he said, okay. And so we were granted time on that. And there we are. So there's me and there's Kirk, and then this is Chris Angelos, who's a board member up there and has privileges on the big scope. So 30 inches, way bigger than 8 inches, and that yet gave us enough firepower to get some pretty good data. So I've got my Wattec 910HX low light level video camera in the eyepiece, and I'm feeding it into data there. Kirk is back here helping with electronics and stuff, because and computers and things, that's kind of what he knows. And then you don't see Chris here because he's back there and he's working on the guiding the telescope, controlling it. So, did we get good data? Yeah, we got great data. Now, there were some other observers, but you can see us up here near the top, number 1, so that's me, Nolthenius and Angelos. And we just got a small bit, and that's actually the most valuable one because it really pins down exactly where the planet is. Now, of course, we had a mission, the New Horizons mission that arrived at Pluto in 2015. You might think, well, of course, you got to know where the planet is. Yeah, but not accurately enough. What you really want is to know perfectly where it is, so you could put people at just the perfect place to get grazes or whatever kind of data that you're trying to look for. And you could see from the path back here, if I go back, there we go. This is the predicted northern limit, the blue line. The red line is the one standard deviation error in where it might be. So it's a little bigger than you might think. This is the software that we were using back then. That's now 6 years ago. This is called LiMovie, Light Analysis Movie. It's software that was written by a Japanese astronomer a long time ago who's no longer around, and nobody knows how to do any modifications to it. So we now have PiMovie, which actually is a lot better. But LiMovie was the ancestor. And what you do with that software is you put an aperture over it, and it'll measure everything in there as your star, and then everything out here in this annulus, it's going to be blank sky. We can do that a lot more artfully these days because it may not be true that that's all sky. There might be a star in there. You might not want a circle. You might want to have something adaptive. Anyway, that's software stuff. Anyway, back to the event. So there's our comparison star in purple. Obviously a lot of scatter. Remember, this thing is 15th magnitude. How many people here appreciate how faint 15th magnitude is? Some of you, yeah. Now, if you don't know magnitudes, the bigger the number, the fainter it is. And 15th magnitude is enormously faint. The stars you're looking up tonight, out here in the parking lot, maybe you'll see magnitude 2, magnitude 3 if you're lucky. So 15 is in its logarithmic scale. Anyway, because we had a 30-inch telescope and we're in a dark site, we actually got pretty good data. So there's our data. And now if you look in, you'll see, first of all, there's point-to-point noise, and that is noise. But then there are places where it's up and it stays up, and then down and it stays down, and then it comes back up. And these are actually real. Those are like the sun setting through layers in our atmosphere, and it kind of focuses and defocuses, and you get brightenings and dimmings that have to do with refraction through Pluto's atmosphere. And of course, we don't have any other way to try and keep track of Pluto's atmosphere except by occultations. So this data has been submitted. They're still analyzing it, frankly. It's been a long time. Keep waiting for the paper to come out. Still haven't seen it. Okay, another great thing with these events is you can discover binary asteroids, or if you already have a known binary, you can try and improve the nature of its orbit, the parameters of its orbit. So Kirk and I have been involved in chasing after several of these. And so let's talk about those. So here, May of 2021. Whoops, is that me? I'm good? Okay. Yeah, I can't quite see on top there, but May 2021, Dave Galt and Peter Nosworthy in Australia were watching this asteroid named Arecibo, named after the radio telescope. And they saw it disappear, and then a second later it disappeared again. And they were not together, they were 100 miles apart, and yet they were parallel to the track pretty well. And they both saw the same thing. As far as I'm concerned, that's confirmation, because they had two observers and they were that far apart. They had confirmation that was a new binary asteroid. The first asteroid discovered to be a binary by Occultations. The reason I say that is because there is a prize that goes with that. And they've seen fit to award not just Dave Galt and Peter Nosworthy, but also me and Kirk Bender, because we enter the story next. I'm actually not eligible for any money because I'm not an amateur astronomer, but Kirk is, so we'll see how that goes. Anyway, we're not supposed to be saying this, but anyway, I just told you, so I guess the cat's out of the bag. We just heard about this very recently. So 3 weeks later, whoops, wait a minute. Got to go back here. Yeah, so now this is my light curve of another occultation. Dave Dunham called me up and said, hey, these guys have just discovered a binary asteroid, and I've done some calculating, and there's going to be another occultation by this asteroid, and it goes right through Central California. Now, the bad news is it's on a weekday, and it's at 4 a.m., and it's like 150 miles away. So I did have to pause for a moment, but once that gets kind of going in my craw, then I'm going to go for it. And Kirk has always been, anything I've asked, he's always said, yeah, let's go do it. We did. We drove all the way down to Paso Robles practically to get this thing at 4 in the morning. And thank God we actually got a double occultation. Both of us did. In fact, we got a better double occultation set of data than Peter and Dave did 3 weeks earlier, because we were further separated. And we just lucked out in where the asteroids were. We really got them perfectly. And then 3 weeks later still, now this is not to lead you into thinking these occultations happen all the time, because they don't. But this is unusual. So we had another occultation by the same asteroid 3 weeks later through California. This time it went through the Sacramento River Delta area. High winds up there, and we had to deal with that, but we sort of did. We got data, we got an occultation, but we did not get a double occultation. It may have been that the objects were actually on top of each other. That's quite possible. In fact, I think that's probably likely. But I was wondering why I didn't see a binary event, and Kirk, who had even better data, I put him at a site that was even more protected from the wind, as it turned out, and he got even better data, but no moonlet. So then I said, well, darn it, where was the moonlet? And I sat down and tried to calculate exactly where the center of the moonlet could be and still have it not be visible by the people who got data. So I figured it had to be somewhere in these hatched areas. Or it was like dead on top of us so that you couldn't even tell. That is one other possibility. Okay, now for the same event, same asteroid rather, now 3 years later. So this is now just less than a year ago. Arecibo again occulted, a decently bright star, and this time it went across the desert. So there's Needles, California, and this is into Arizona. And it was on a Saturday. Oh boy, Saturday. So I got a college van. I said, look, we got big science to do, and I've got students. I didn't really tell them it was a former student, but anyway. And so this is college education prime. We're doing big science here. And they said, okay. So they gave us the van, 1,000 miles of driving we put on that van that weekend. And there were some other observers in Arizona, and there was a couple of others in California. And again, we got great data. In fact, of course, you always want to make use of a big trip like this, and I scoured through all the predictions, and I found 2 other asteroid occultations that were happening on the drive out. So this event happened at 2 a.m., but at about 11 p.m., there was 2 occultations whose paths crossed right there on Interstate 40 at Kell Baker Road. And so I said, let's go there and let's try and get these 2 events. Most of these, well, anything that has a name like this, 2001 QH60, you know that's not a super well observed asteroid. And we don't have a great orbit for it. And I've learned the hard way that the 1 sigma error bars they put on the shadow are way too optimistic, and it really could be more like that. In fact, the first event, we both got good data, and it was a miss. We had 2 misses. The second event, an hour later, however, and then Kirk ended up being in the wrong place, got a miss. But I did get a short occultation. So there's my data. There is the asteroid and drops to 0 and comes back. Very short, 0.56 seconds. But it satisfies the false positive test pretty well. Now, the other thing about this particular occultation is we had more challenges, and that was fires. So there was smoke from wildfires in Southern California that was blowing up north, and this was the smoke prediction. There's Needles, but our prime site that we had laid out was down here where the fires were. And we finally just had to give up on that. And I said, well, it looks like there might be a chance that the smoke will blow north enough that we could be in the clear from Needles. So let's go for there. Of course, you have to be on the path. There's the path on the other half of the slide here. So this is the track of the asteroid shadow. Again, these asteroids are tiny. They're like, 3 miles across for the whole shadow. And you can see all the fires. Look at all these fires. And there's this smoke prediction. So it's like, well, that's not fair. I mean, it does nothing but go right across our path. But it looked like we might have a chance if we went all the way to the Colorado River, which we did. And we got lucky because it turns out that smoke kind of started arcing and moving west. And we really went through the worst of the smoke well before we got to our occultation. So that was good. So we avoided the smoke, and it was all good. Now we're set up for the main event, 2 a.m. This is me. I'm still in my running shorts at 2 a.m. under a clear sky. It was hot. In fact, as soon as the sun came up, we made sure to try and get back in the van and get on the road because it was going to be too warm. But look at the data. We got great data. Look at the confidence limits on the disappearance and the reappearance time. Pretty darn good. Kirk got good data too. There's Kirk's site, just at the extreme southern end of Needles. I was a little bit further south. And you can see his data is pretty good too. And of course you can't read it, but this is actually the disappearance time, and there's the reappearance time, and there's the duration for Kirk. Kirk's occultation was a little bit longer, 0.34 seconds. Actually, a little bit shorter, than mine. Mine was 0.56. And so all that was put into Occult4, which is software that can calculate the orbits and try and fit them as best as possible. And Dave Harold wrote that software, and Dave Galt is the primary user of it, so those two are kind of a team for doing this stuff. And they determined that the best solution for the positions of the two asteroids was this. This is another observer, and these are a couple of missed stations from David Dunham. And there's Kirk and there's me. And so both of our events, both of our tracks went only across the moonlet, the new moonlet. So we got that specified pretty well. Okay, now is an even more important one. I'm trying to go through these chronologically. This is November of 22. And how many of you know about the DART mission? A few of you. Okay, the DART mission was a NASA mission to test what do we do when we find a big asteroid and it's going to hit us. So you might think, oh, well, we'll just call up Bruce Willis and his oil riggers and they'll go blow it out of the sky, right? No, he's not into that anymore. Okay, so we're going to have to go there without people. And in fact, it's way safer to do it without people. So what we did is we chose this very lightweight, but probably more typical in terms of what might hit us. Not giant asteroids. I think we've mapped out all the giant asteroids that could be total planet killers. None of them are going to hit us in our lifetimes. But probably, unless it comes out of the Kuiper belt or the Oort cloud, then it could be a bad surprise. But lightweight ones like this, and it's Didymus and its little moon Dimorphos. But they're tiny. They're like a kilometer across. So trying to get inside the path for an occultation by these objects is itself pretty tricky. But we're going to go out the desert. We're going to do it. It was in November, so we didn't have to worry about heat. In fact, temperatures were just fine. And what do we got? We got a nice occultation. The star was bright enough. It wasn't that bright. It was 11th magnitude, but you know, in terms of these things, that's actually not bad. 11th magnitude, and that allowed me to put this on a setting of 1x. 1x means that I am going to log, download, and set every single interlaced field of an interlaced total frame. Mostly you look at frames, but if you do one field and then the other field and the next field and the next field, and then you can get twice the time resolution. So that's what I chose to do because I knew it was going to be a very short event. And the star was bright enough that we could do that and get away with it. And look, we got really, really tight data. Kirk was a short distance away. Now, there's this devilish pathology, which anybody who's owned a Meade telescope and then a Celestron telescope has probably run into. And that is that they are powered by these barrel power plugs. And they both fit in. Oh, I'm seeing some people, yeah. They both will fit into the Celestron telescope. But the Meade one has an inner diameter that's a little bigger. And so it will hit the little center plug inside the telescope, but it won't make good contact. So all you have to do is look at it wrong, and boom, you've lost power. Your telescope. And unfortunately that happened to Kurt, and when you lose power you've got to start totally over from scratch. You've got to do a new 2-star line, and since he wasn't even sure why this was happening, we kind of figured it out later. He actually wasn't able to get data. So that was sad, but there were other people who were on the track and did get it, and in fact there was one person who even did the heroic mission of going out and trying to get the moonlet. And we didn't know exactly where it was, but he made a pretty good guess, and look at that, he got the moonlet. So this was the first post-DART mission data that logged both the primary and the moonlet. So this is really crucial in now being able to set the new orbit after the impact. Because after the impact, you may say, well, don't you know the velocity? Yeah, we know the velocity, but how much of that energy went into just scattering stuff? How much of it went into actually a momentum change of the total asteroid left over? So you don't really know how it's going to change the orbit unless you do it and then monitor. So we're in the process of trying to do that. Every occultation that happens by phaeton gets a lot of interest, and this was a big success. So afterwards we slept well. I cooked some eggs and cowboy toast, and we had fun. Then we went to Mitchell Caverns and checked out the caverns. That was a lot of fun. And here's a paper published in ANA in 24 on this new binary asteroid Arecibo. They determined the density of the primary and the secondary to be, look, they're different. 1.6 grams per cubic centimeter versus 1.2. Now, 1.0 grams, you'd probably say, oh, most certainly this is just pure ice. Or else it's just a magic mixture of fluff and then rock to average out to the density of ice, which is 1 gram per cubic centimeter. What's interesting, though, is these two objects aren't just identical. They're clearly different. So that brings up questions of where they came from. So not only do you discover new things, but you pose new questions. Okay, here's our next special event. This was another great adventure. Euripides. This is the largest asteroid of the Trojan asteroids, which are orbiting in Jupiter's orbit. So if Jupiter's up here in its orbit, then the Trojan asteroids are 60 degrees ahead and 60 degrees behind Jupiter, and they follow Jupiter as they orbit the Sun. And they orbit again in 11.8 years, just like Jupiter. They're settling into these shallow little gravitational wells, as we call them, that stuff can collect into. That's no doubt going to affect how these things form. We don't have any close-up photos of any Trojan asteroids. The Lucy mission is going to get there very soon, this year, and we want to know what we're going to find, and we also want to know whether there's any moons around some of these, like Euripides. Because if there's a moon there and you don't know about it, you could smack right into it. We don't want that. We do want a moon, though. That makes it interesting. You just want to make sure you don't slam your spacecraft into it. So this is a super high value target, and there's a whole set of tracks that were laid out by a group called the Recon Group. They have actually given pretty good telescopes and equipment for a whole bunch of mostly college or even some high school students all along the backside of the Sierras, all the way up into Oregon and Washington. And Kirk and I are now part of that group too, even though we're in Santa Cruz. But weather was a challenge. So we had our first storm of the season coming in. Everywhere west of the Sierras was cloudy. But the forecast said that the rain shadow of the Sierras was going to give us a chance. But every hour I was checking the new weather forecast. Does it look good? Does it not look good? It's kind of a big commitment to blow off my Astro 8A observing class on Tuesday night and say, okay, gang, go home. You know, me and my asteroid chasing buddy, we're going to go out and try and get this asteroid. Of course, nobody cried crocodile tears when I made that decision. But it actually was kind of like, do I want to take my old RAV4 up over the Sierras during the first storm of the season? Are we going to get snowed in? Is this the last time we're spring frozen in our car? What's going to happen? I don't know. Nothing that terrible happened. Actually, we kind of survived. We did more than survive. We actually got some data. So these are the tracks. This is my track, and I set up here at a cemetery, which I hoped was not going to be like a sign, you know. And then Kirk, I put Kirk at the Mono Lake Visitor Center, which is right there, right on that track. So there I am helping Kirk set up. It was rather windy, so we had to be choosy about where we set up. Fortunately, there's some juniper trees there at the parking lot of the Mono Lake Museum, and Kirk got behind those and got data of clouds. There's a shot I took of me at my site, and you can see these clouds. And these clouds were random because they were just coming over so rapidly. There's no way to like, oh, I think the cloud pattern is this way. I'm going to like move another half mile this way. No. It was totally like running through a minefield, and you don't know if you're going to step on something or not. What happened? It turns out there was a big cloud coming in, and Euripides was coming in too onto this faint star, and I could tell it was going to be a real close race. Who was going to get to the star first? And I was really lucky that Euripides actually got to the star first, and with just 1 second, literally 1 second before the cloud got there, I got the occultation of the D. I got the disappearance. So that was our big data savior. I did not get the R. The cloud took the R away. So there's my chord. So I got the D. I got no R. But you can see how perfectly it fits with a circular shape to this object. And that actually might be telling us that this is a giant rubble pile, maybe even a dust pile. We don't know its mass. But if it's in a shallow gravitational well, it may just be that these Trojan asteroids form by very slow velocity agglomeration of dust and dirt and pebbles and whatnot, rather than some violence out there. If so, then you would expect even small objects would look very spherical. And luckily I got that D because that was the one that really told us what the shape was. The other observers had misses, and then there was a couple north of me who did get good data. So yeah, we specified the position accurately, so the spacecraft people were happy. So even though Kirk was clouded out, we celebrated. We went off and did some aspen photography in June Lake, and then we went to a pub. And while we were at the pub, Kirk got on his iPhone, and there was a what was that, Kirk? Was that a meetup? Was it a...
I think it's Slack.
Slack, that was it. So yeah, it was a Slack arrangement, so we could all find out how we did. And so that was what Kirk's doing there. Started raining while we were having our beer, and snow was coming down, and we thought, we better get home because we got to go back over Tioga Pass, and we don't want to get snowed in. So all that went well. And then I put this slide in too because Kirk had a interesting observation 2 years ago of this asteroid named Repsolda, and it looks like there is a occultation. Now this is several different apertures. The different colors don't mean different stars in this case. They're actually different apertures of the target. But they all show what looks like an event here. Now, moons of asteroids are rare and uncommon, and binary stars are more common. It could be evidence of a binary star, or it could be a binary asteroid. We don't know. But every time I see a Repsolda on my predictions, then we haven't seen it since, but we're going to pay special attention, and others will too, because it's been flagged now as an object of interest. Okay, now our first Kuiper Belt object discovered after Pluto. Pluto, of course, was discovered in 1930. The first one discovered, unfortunately, came after Gerard Kuiper died. He died in the 1990s. But here in 2002, we discovered the object Quaoar. And through occultations, it's now discovered to have 2 rings around it as well as a moon. So that little moon there is called Weywot. And there actually was an occultation We don't know the path very well, and it was somewhere in California. Kirk and I went after it. We didn't get anything, but then there was the rings, and could we see the rings? The thing about these rings is they're very bizarre. They're out beyond the Roche limit, and rings should not be stable out there. So how did they form? What are they doing there? We don't know. They were discovered at the CFHT big telescope on Mauna Kea, the Canada, France, Hawaii big telescope. It's forget how big it is, but anyway, it's huge. It's way bigger than anything we have here. And you can see that there's a nice deep occultation here of ring number 1. And then on the opposite side, though, there's only a very shallow occultation. So that's telling us that ring number 1 is not uniform. And frankly, you might be surprised if it were. If it were inside the Roche limit, the breakup of non-gravitational, well, the breakup of gravitationally held only objects is inside the Roche limit. You guys want to hear briefly what the Roche limit is? Yes. Yes? Okay. I never know what my audience is like going to be interested in, but imagine a pile of dust. Just dust. Not a rock, dust. You could ask, well, where would I have to put this near a planet way over there such that when I finally got close enough, the tidal stretching would overrule the gravitational self-attraction? That's the Roche limit. So things that are only held together by gravity, like rubble piles or piles of dust, are going to break up inside the Roche limit. If it's a rock, though, it's going to stay good even inside the Roche limit. If it's outside the Roche limit, you wouldn't expect any rings at all. Not unless they're brand new, just got caused by some tragedy, and the stuff hasn't yet disappeared, gone off. So these rings are a mystery. We don't understand them, but they're definitely there. The first ring was discovered during this earlier occultation, which was visible also in California. And Kirk and I got our most difficult occultation ever on that night. So look at the star. The star is 15.2. And we didn't have access to Fremont Peak or to any other big telescope. We just had our 8-inch telescopes. So how are you going to do that? Why did we even try? I wondered, but I said, it's a big event. We got to try it. Who knows what'll happen? Let's do our best. So we went up to Bonnie Doon, got into nice dark skies, and oh my God, we actually got a detectable event. Now you might look at that and say, Rick, that's pure noise. No, these points are lower than these points. Right? Say yes. Okay. Anyway, that's what Pyote said. It's our statistical, it tells us, okay, you got a detection or not. And it turns out when you use, so Kirk got data like that, I got data like that, and when it was combined with the big telescopes, oh boy, it fit perfectly. So there's Kirk's data. Kirk's data is a little better. By the way, Kirk's got equipment on loan from me, from Cabrillo College. It just turns out that the low light level camera that I gave Kirk is the best camera of any that we've ever had. But that's okay, because Kirk is a top observer. He's always come through, and so okay. If he ever starts messing up, I might repossess it, but anyway, he hasn't. So, but yeah, his data's better. So look at that. Look at the target. You see it? Right there. Yeah, I know. Now, if you'd told me beforehand, so I'm going to get data on that, give me a break. But now there was a break, and that was this event was supposed to last for 44 seconds. So that's enough time to take pretty long exposures, get a 15th magnitude object to show up barely, and get enough points inside of it that you can statistically differentiate it from pure noise. But that's definitely the faintest object that we've ever gotten. So look at this. There's our data. It fits perfectly with this perfect ellipsoid defined by these other observers here. There's the Gemini telescope on Mauna Kea. There's the CFHT telescope. These are two more big telescopes. And it fits a nice ellipsoid. So Quaoar is not round. It's ellipsoidal. From rotation, possibly. And there's the rings. They're outside the Roche limit. What's the deal? Saturn's rings are all inside the Roche limit, like they're supposed to be. So is Jupiter's, Neptune's, Uranus. But not Quaoar. We don't know why. Now, we got one more Quaoar occultation. Quaoar actually, slow as it's moving, it's going right through the Scutum star cloud. Scutum star clouds. I see some people saying, "Oh yeah, that's like the brightest part of the Milky Way." So when you photograph the Milky Way, you see all the dust lanes, and there's some big blob. There's two big bright blobs. One of them's in Sagittarius, one of them's above that in Scutum. It's a Scutum star cloud. So it is great. We're not going to have it in the star cloud forever, but for the past few years and the next few years, there it is, and that means there's going to be occultations. Time will come when it'll be out there in Leo or something, and then good luck trying to have it go in front of a star. I don't know how many thousands of years it takes to go around, but it's a long time. Okay, there's the shadow path for another occultation. This one now is in 2023. By this time, I had gotten up the nerve to call up the Monterey Institute for Research in Astronomy, thinking, they might actually they might want to help us do this, because they're all privately funded and they're not associated with a college, and they want to show their donors that they're doing good science. And they are doing good science, but mostly it's polarimetry. And here, this is something completely different. And lo and behold, they were more than eager to have us come up, and they gave us 2 nights on the big scope. They love the idea of expanding their science opportunities, so we're given 2 nights. There is the path of the star by Quaoar. But Rick, it misses Quaoar. Yeah, I know. But it goes across the rings. That was really our goal. That's why I didn't trust us to try and get that with our little 8-inch telescopes. I thought that would be hopeless. But to get the rings, maybe we could do that with the 36-inch. And so we did get data. They gave us 2 nights, and luckily on the first night there was another occultation, this by the asteroid Eunomia, one of the early, larger, more famous asteroids, a named asteroid. That was discovered back in the 1800s. And it went in front of a star. Now, Eunomia itself is fairly bright because it's a big asteroid, and that means that when the star got occulted, you didn't lose very much light. So the total depth of the drop here is only 1/10 of a magnitude, which if you were watching that with your eye, you couldn't tell that at all. But with enough data points, you can pull it out. So we got great data using the instruments we're going to use the next night. It was a good shakedown for our equipment on this big telescope. There's Kirk. Again, Kirk's got the better Wattec camera, so we put him on the big scope, the 36-inch. And they also have a smaller 14-inch Schmidt-Cassegrain mounted at the bottom, and I put my gear on that. So we did get 2 separate sets of data. Can you find me in there? Yeah. This scope is amazingly outfitted. They've got every possible instrument that they could imagine. And all of them need power, and they need data cables, and they need control cables, and it is truly a rat's nest. And I put the slide in because it shows one of the pieces of software that we use to do our work. So this is called PyMovie, and that is Quaoar. And all the light inside this mask is collected and counted as light from the asteroid. There it is in the aperture, And inside the aperture, what the software will do is it will actually migrate around and try and follow the star as the seeing variances cause the star to move around a little bit and twinkle a little bit. These other masks are on brighter nearby stars. The yellow ones are used for tracking, so that if your object disappears, here's what you don't want to have happen. Suppose this was a more regular occultation and this was going to disappear entirely. What you don't want it to do is suddenly go crazy and say, oh my God, where'd it go, where'd it go? And start wandering around and grabbing onto stuff that's not real, right? You don't want that. So when it disappears, falls below a certain level, then it just says, okay, I'm going to just do whatever my two tracking stars tell me to do. So it just follows along the tracking stars. Look at the precision in time here. 8 hours, 45 minutes, 36.6856 seconds. So those are GPS time signals off the satellites. Now, of course, if you're going to do this well, you need a reference star that you know for darn sure should be constant, but it might not be. There might be little bits of haze and aerosol that go through the line of sight that your eye won't be able to pick up, but the camera will. And so that's our reference star, and that's in green. And what you want to do with the software is you want to smooth. You definitely don't want it to take every single random dot here, because then what are you doing? Well, you're combining with another random dot down here that just has to do with readout noise and random sky noise. Basically, you're adding in quadrature two different sets of noise. You worsen your signal instead of getting it better. So you got to smooth your signal, but you don't want to over smooth it. You want to smooth it just to the point that you think the wiggles are real. The way you try and judge that is you look at this and you say, well, how can I minimize the scatter in all these points? And the software will let you kind of try different smoothing lengths until you maximize the flatness, or minimize the noise. So that's really interesting. And I'll even let you offset it. Maybe there's clouds going through, and the clouds hit your target at a different time than they hit your reference star. So then you need a time offset, right? So you can do that too. So Bob Anderson really did excellent work in programming all this up. This is a paper, so you can get co-authored on a paper in a big journal if you do this right. So we're co-authors on this from our observations at Bonnie Doon, and I was at UC Santa Cruz for this event. Okay, and the last one I want to show is this is a new discovery of a new binary asteroid. Again, it's luck. You don't know how to go after a new binary asteroid, but Kirk and I go after a lot of them, and so luck comes to the prepared mind. How does that go? I forgot who said that, but anyway. So yeah, actually, I discovered a new binary asteroid last November. And it was named after Martin Schmidt, who I had the pleasure of actually meeting while he was still alive. He was the astronomer at Caltech who first figured out quasars. And I met him early in my career when I was still a grad student at UCLA. And he came to, we all got together for a big astronomy meeting. And so there's the track. And you can see it goes right across Cabrillo College. So that's where I observed this thing from. I said, oh, this is great. I can just do this at my home college. And the weather was good. And the only real problem was that we had a full moon. And the full moon was 9 degrees away from the target. So, but the star was bright enough. I thought, well, I could still get it. But to my amazement, the star disappeared. Not once, but twice. And I started this, I said, yeah, and then there's another moment. I think I saw it disappear twice. It took me a while to actually let it all in that, oh my God, I think that was a binary event. It was. And I announced it to the International Occultation Timing Association, and they put it in their message board. And there's a lot of people a lot of astronomers who look at that. And Jean-Francois Gaut and Mathieu Conjat, who's in France, heard about it, and they had the gear to now monitor the asteroid itself, which is really dim. It's only 17th magnitude. But they had good enough gear to be monitoring the brightness of the asteroid to see if there was some kind of periodicity in the changes in the brightness of the objects. And in 3 consecutive nights, look what they found. Well, this is actually all Jean-Francois. Somebody here knows Jean-Francois. Who was it who talked to me about that? Maybe that was only Chris, who's not here. Anyway, look at this. Deep eclipse. This is not passing in front of a star. This is the 2 asteroids passing in front of each other. 23.17 hours apart. Wow. Now, the question is, well, if one passes in front of the other, is the orbit round enough that when it comes around halfway, do we get another eclipse? And this is where Mathieu Conjat and his data in France comes in. So he actually got a secondary eclipse 12 hours before. And then Jean-Francois got a primary eclipse here. So at that point, this discovery was confirmed. Prior to this point, though, I was, well, we have an auditor in the chain here who is a pretty strict taskmaster as far as reporting a discovery of something, Dave Harold. Okay, it is true that there are a lot more binary stars than there are binary asteroids. And so if you see your target fade twice, how do you know you're not just going in front of 2 different stars? Here's how you know. A total star has got to have, at best, 50% of the light here and 50% of the light here. If this one's got 70% of the light, then this one can only have 30% of the light. So your light curve cannot go below 50% for both events without being a binary asteroid. See? See how the math works on that? Well, now this already verifies it, but I didn't have this data yet, so I went through all the trouble. Actually, you know what? Because I did this right before I left, I didn't put in those slides. But there is a website you can look at other slides that show. I went through every star in the field, and I found stars that were less than half the brightness, even on that super bright sky. And I put my apertures on those, and I ran those through the software, and I could prove that the depth of both of those eclipses went deeper than a half. And I said, well, why didn't they go all the way to 0? Well, they did go to 0, but the problem is that the sky itself was so bright that 0 wasn't really 0. It was like, a bright sky. But it was deep enough. Okay, and then the very end of this story is that turns out there was another occultation by this star just last month. Well, a month and a half ago now. And against astronomical odds, the path for this tiny little 4-kilometer path intersected the path from November of last year right at Cabrillo College. Like, the odds against that are astronomical. So I thought, wow, this will make a great story. I'm just going to stay right here, and we'll have my team, set up in Santa Cruz. And so I found out sites and blah, 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 and we're ready to go. And then the weather forecast said, looks like, this is actually not looking so good. And like 2 days before, I said, I don't think we can observe from here. We're going to have to go east. So I laid out stations now at Mercy Hot Springs. Some of you might have gone there for star parties in the past, a great spot. Well, we got out there and the clouds were still coming. The weather forecast was not good. And so we basically had to just step on it and gun it as fast as we could to try and get ahead of this advancing cold front. And now, this is Bernard. He's my top student this semester, and this is Sandy, who's another top student. And they both got into this, and Bernard, these guys left a little ahead of Kirk and I, so they are actually the advanced team. And Kirk and me a little bit, but mostly Kirk, and then these guys were all on the iPhone while we're trying to drive, out in the middle of nowhere, trying to stay on the path, but also get ahead of the clouds. We eventually ended up at this place called Helm near San Joaquin, right in the middle of the Central Valley. I mean, we ended up driving like 250 miles this night when I thought I was going to drive maybe 5 miles. And then there's Kirk. And so we're all smiling here, except for me. I'm looking at my camera, making sure it works. But yeah, because we had a success. Bernard was in the perfect place, and he had the biggest telescope. He had a 10-inch telescope. And I wish I had on YouTube his expletives, no. His excitement. Because he actually saw the star much brighter wink out clearly twice, one after the other. He said, "Oh my God, oh my God, oh my God, I got it." And now Kirk got it too, but he only got one occultation. So the other one did not get occulted from Kirk's site. I was north of Kirk, and I got 2 integrations that are at 0, but there was some others that were at 0, and it was perfectly lined up with Kirk, but it means the asteroid would have to be a little bit oblong. I don't know whether it was real or not. Okay, I don't know. We're waiting for a verdict on that. If it was a miss and just noise, well, that's okay. The real data is from Bernard. And then Sandy had power troubles. Actually, he had the same power troubles. He learned the hard way as well as Kirk did a few years ago. Okay, so how do we get this data? What kind of gear do you need? Well, first of all, you need predictions. So there's software called Occult Watcher, and it's free. Occult Watcher desktop. So you download it, put it on your screen, and every time you fire it up, it will go through this massive database called Occult Watcher Cloud. It has every occultation anywhere in the world. And it'll find the ones that are close to you and that satisfy your filters. How high a rank is this? I don't want the sun to be up. I don't want it to be too low in the sky. You can have all these filters. And then it'll show you your events. So I did this yesterday for me. There's actually a couple other events on here. But you can see the only other event that I haven't tried yet is this one, Montesquieu. And it's on Monday morning at 4 a.m. I'm probably not going to try it. I don't get enough sleep as it is. But anyway, it is close enough to give it a shot. And then, if you click on it, it'll tell you all about it. Here's the event time. There's the duration, 1.0 seconds. That's actually pretty long. When we see a 1.0 second event, we say, whoa, that's good. Magnitude 13.4, yeah, it's not so great. 19-degree altitude, that's not so great. The moon is up, and it's a big moon. So, I don't know whether I'll try that one or not. Then, in Occult Watcher, you can also just click and say, make me a chart. And it'll go to this planetarium software called C2A, which you'll download onto your computer in like no time at all. And then it'll plot a chart. And so there's the chart. This one I did for the Pluto occultation. So there's Pluto, and there's our target star right on top of it. This is the size of the chip in our little cameras. And so you tune that, and basically I just leave it alone because almost always I use the same stuff. And that tells you exactly what the orientation is. This is so valuable in trying to find star patterns. And still, sometimes I fail. Sometimes I'll look at my stars and I'll look at my chart and I say, I don't see any matchup at all here. But you look for the bright stars and you star hop and figure out, oh, okay, I think I see where I'm looking. We use a Celestron 8-inch telescope. It's good to get as much light as possible on each pixel. So we use a focal reducer, turns our f10 long focal length telescope into a 1/3 of that, to f3.3, and makes the stars look much brighter. Also makes the sky look a lot brighter, so sometimes you don't want to do that, but mostly you do. And then here's our little camera. It's an amazingly small little camera, Wattec 910HX, but it's still the lowest lux, the most sensitive camera out there. It's not very high resolution. The pixels are big, 640 by 480 or 720 by 500 or something like that. Kirk would know. What is it, Kirk?
720 by 480.
There you go. And that's good enough,
NTSC, The PAL one.
The PAL is yeah, and the PAL one is the one they still make. They don't make the NTSCs anymore. And I just like to deploy out of the back of my Toyota RAV4. And I've got the whole, I'm like a sprinter as far as like all the skills down. So as soon as I turn off the key, I know exactly what to do. And if I don't have any trouble, I've actually set up and been on target in as little as 18 minutes. Kirk likes an hour. But that's because he's super careful. And what that means is that the batting average, which I also keep track of just for fun, Kirk always gets a better batting average than me. I managed to fumble, not very often anymore, but still I fumble more often than Kirk. And I still like the old camcorders. These things will not only act to take video out of the front lens, but there's a input, you can just have it record from somewhere else. So it'll put on your mini DV tape, digital signal now, from our camcorder, or from our Wattec camera. There's a little external monitor, there's a little remote control so you can operate it. Extra tapes and batteries and whatnot are always good. And yeah, last year I got 91 successful events. 33 so far this year. I think Kirk might have 35 or something. The IOTA website has the links to all the software and the instructions you might need if you want to do this. And there'll be an asteroid event at least probably once a week. It goes right over your house, so you don't have to travel if you don't want to get into it as much as we are. The IOTA message board is great. You can post questions, get answers. I always go to the message board to see what the latest is. Sometimes an astronomer will, pipe in and say, oh, there's an asteroid by a Kuiper belt object that's coming over the western U.S., on such and such a date and time, and really need observations. We really hope you guys can get out there and get this. And if that happens, then we do everything we can to do so. Anyway, there's the gear that I use. And there are other options that are newer, and I'll show you that in a minute. But anyway, this is what we use. And it all adds up, including the main thing, which is a telescope. Celestron Nexstar 8SE telescopes. Now, I've got $1,200 here, but they're more like $1,800 right now. So there's that. But you guys are all Silicon Valley people, so this is cheap, right? And then Mark Simpson has done something interesting. He's made a whole new system, completely self-contained. This is the Asteroid system. It includes the camera, and all you got to do basically is plug in a USB card, and it'll record your digital video onto the USB. And you just hook it up to your eyepiece, and then you put it into your computer. And of course, the software I just talked about is free. I don't think the camera's quite as sensitive as the Wattec, although there's not total universal agreement on that. I might buy one. I've still got a little bit of money left in this year's budget. Reducing your data. So I've got a whole big PowerPoint that I made and slide set for my team to learn about it. So I've got some new members in the team, and you can click on that if you want. But just really briefly, you got to install Python programming language into your computer, because PyMovie and Pyot are both the two programs that you need to complete the task, and those are Python programs. You set apertures on your target. So our target is here, and then that and that is reference stars. So here's our target. And you can even change the way the aperture is, the mask. If you got a whole lot of wind shear and you've got a long integration, then each of your images, maybe the star is kind of a weird shape. You can tell it, okay, put on a dynamic mask, and it will actually calculate exactly how to make the mask to maximize the signal to noise for every single frame. Takes longer, better go have dinner, while it's working. But there's that. There's also a way to stack the frames, and then maybe your star's out of focus. Okay, that happens to me sometimes, especially if I'm in a hurry. And my stars are actually little crescents. They should be little donuts, but they're not even donuts because the secondary mirror is not perfectly aligned, so they're more like crescents. Well, then you want to have an aperture that's shaped like a crescent. So you can stack a whole bunch of frames and tell it, okay, find the best mask for a stacked image, and then use that. So that's a tight mask, a TME mask, and so you can do that. Mostly just a circular mask that it stays centered on the stars is good enough. But it's really, really good software. Okay, so now you've got your photometry, which is basically a CSV file, a text file that's, in CSV format. And it's just numbers for every target. So there's your target, and there's your tracking star number 1, your tracking star number 2, your reference star number 1, number 2. Put as many stars as you want. Of course, it'll take longer. And every one gets a column. And now what do you do with that file? So that's where you use Pyot, or some people call it Peyote, but since I'm not a drug person, I don't like to do that. I just call it Pyot. I don't really know how to pronounce it. And then Pyot will look at all that data, and it'll ask interesting questions like, so you really think you got an event, did you, Rick? Well, there's a little bit of a dip here, and it's sort of in the right time. Now, is it noise or isn't it? You want to have some statistical evidence that it's real. You don't want to just put your hopes and wishes on it, right? So what it will do is it'll do 50,000 iterations, 50,000 Monte Carlo experiments. It'll take all the data points and it'll just shuffle them up randomly. And then ask, how often do I get that many low points all next to each other? And it gives you a probability. And if the probability is very, very low, then it'll say, yeah, that looks like a real event. If it happens to line up with what you already know is the proper time, and I think that's the right way to do statistics, is Bayesian statistics. You should put in your priors. If this thing happens somewhere far away from where you are pretty darn sure the asteroid occultation probably happened, you better take another look. Maybe there's dead pixels around there. Maybe there's a cloud you didn't correct for well enough. Maybe you bumped the tripod. Who knows? There's a lot of different ways you can have things go wrong. And then I have my team send me all of their data. So I'm just going to go here because there is Lila. This is an event we did about a month ago. And there's the finder chart for it. And there's the time, and there's the duration. Wow, that's a long one, 20 seconds. That is really long. And there's my data. So there's my longitude and latitude, and there's what? Okay. Where did it go? I clicked on this and it came up here. Well, Whoops. Uh-oh, now what happened? Well, I don't want to ruin things. Maybe I should just forget about that. We'll go back to the PowerPoint. Anyway, I have people send me their data, and I make a nice web page, and it's got all of our light curves, and it's got their narrative, and it's got the timings. And that way, when the auditors look at this and decide, should we pass this on to the astronomy databases, if they have any questions, rather than bugging me, they can just go straight to the web page, and hopefully everything they need is right there to make them satisfied. So these are exciting, and they're important, and they're real science. They're not just for fun, but part of the fun is that you're doing real science. There's a million things that can go wrong. Believe me, my batting average was really poor for years. My buddy Carl Van Anen, some of you might have met him. He used to run the planetarium at De Anza College for many, many years. He's still president of the Pacific Planetarium Association. And I lent him a bunch of gear too, and so he's getting into this. He's just now getting to the point where he can do his own reporting and reductions of data. Yeah, it's a steep learning curve perhaps, but it's fun. And then the last slide here is, this is an event tomorrow night. This is the planet Uranus is going to go in front of a 9th magnitude star, but it's really, really tough. So I don't want to get anybody too excited. The sun altitude is -10, so it's definitely still twilight. And Uranus is in twilight. It's only 23 degrees up in the west. The target star is only 1.5 arc seconds from Uranus, which is 80 times brighter. So I've told myself that, if I have time, I'll go to Cabrillo Observatory, see if I can hook up the WATEC to our 12-inch. If I can't do that, I'll probably still try it with the 8-inch just to see what I get. But 1.5 arc seconds, I mean, our seeing blur is more than that, so I don't know. And now, this is not to try and record the planet occulting the star. That's impossible. But there is the epsilon ring, the densest of the rings of Uranus. That's what we would hope maybe to record, is a few seconds of the star dimming down as it goes behind the epsilon ring. But what are the odds? Anyway. Okay, so that was pretty long. Okay, so I went over an hour. But if you're not totally ready to run home, maybe somebody has questions? I don't know. Maybe you're saturated. That's what I tell my students sometimes. You look saturated. And then I just tell them, okay, see you next week. Question.
So you mentioned you can have good data or bad data and a miss or a hit. And so
Yeah.
what is good data versus bad data look like?
Well, good data means that the signal to noise is good, the scatter's small. And if your asteroid occultation has a really strong, I mean, it'll give you a signal to noise ratio, and it'll tell you like, well, if we take your data, so the modern way they do it now is they take your data with the occultation, and then they take your data without the occultation. And they ask, do those two distributions of points differ significantly? And they'll show you how much they differ.
Yeah.
And if they differ by more than 2 sigma, then it's pretty unlikely that that's noise. It's probably real. That's one way to tell. If there's a lot of clouds and you can't correct them very well and your signal is low, you might just say, I don't think I can call that real. It's suggestive. But yeah, it's basically what noise sources do you have. Sometimes you see a dip that you don't really have a good explanation for, but at the same time, all the light curves are wandering up and down because of fine structure in the cirrus clouds or something. And then it's, what I ask myself is, could I convince the auditors with good reasoning that this is real? And if I think, no, I don't think I could, then I usually don't waste a lot of time on it. I'll just say, okay, well. And I score those in my scorebook as purple, as in Purple Heart, like wounded in battle, but at least you're out there battling. A red, like I sometimes have to give myself, is a fumble. You know, you got the touchdown pass and you let it just go right to the ground. So I've done that too.
I wasn't clear on the plots you were showing. I know that the x-axis is time, but for the y-axis, is that luminance or different points on the sensor? Or can you say just a little bit more about what those plots are?
So yeah, this is intensity. It's not magnitudes. It's a linear thing. The software just takes the numbers. They were read out of the chip, so they're proportional to the number of electrons dislodged in each pixel.
Right.
That's what the vertical axis is. But usually what you do is you also plot it as a sky subtracted. So the software will say, okay, well, we got all these numbers, but there's also random sky in there. We got to subtract out random sky. So it tries to do that intelligently. And I don't know the exact algorithm, but the people who wrote it says even if there's a star that's nearby, it knows to ignore that star and get only clean sky, which is something Live Movie wasn't good at. Yeah, this is time. Vertical is just the numbers that come right out of the photometry. Now, if you have a really tough event, so I didn't say this, but we had, remember that Quawar event, 15th magnitude? 15th magnitude. So we tried also just looking at the raw data without any sky subtraction. Because the star was so close to sky that trying to subtract sky, you're subtracting in quadrature, which only makes it noisier. So for that case, I said, let's see if we can see the event without subtracting sky. And the software will let you plot that as well and do all your analysis on that as well. And that was what got us actually the best signal and actually allowed us to detect those occultations, which were otherwise hopeless, lost in the noise.
But the object you're looking at is moving on your sensor?
No.
So, this is just a single, it's covering the entire sensor?
Well, the asteroid is moving so slowly that over the minute or two that you're taking data, it and the star are merged. And in fact, usually the asteroid, most of these asteroids are really tiny. They're way below the ability to even detect them at all, like 17th magnitude or something.
If you watch it over the course of an hour or something, you might see, if the asteroid is bright enough, you might be able to see the asteroid and the star merge together very slowly.
But it's still just like one point on your sensor? It's
Yeah.
not covering the entire sensor?
Yeah.
Okay.
Well, not one pixel. It'll cover several pixels, but you can determine the size. You get kind of artful about how big to make your mask. I used to think early in this game, I said, I don't want to lose any photons from that star. I'm going to make my mask nice and big, and then I'll get every single photon, and yeah, I'll have to subtract sky. What I didn't appreciate is how much noise there is in sky. And so what you really want to do is tighten up your mask like a lasso until it really just is obviously star. You don't want to lose too much starlight, but you can afford to lose a little and still get actually better signal to noise. And Kirk has done a lot of testing with that, and he always finds that the best signal to noise comes from the really small aperture, only 2.4 pixels. I often go with 3.2, but if my data looks noisy enough, I've learned now to try and go smaller. Does that answer?
Yeah.
Sort of? Yeah.
Can you use the same method to detect the transit of exoplanets?
I would. The same equipment you're talking about? The same equipment?
And the same, your way of recording the movie, looking at the intensity curve. So can we use the same method to detect occlusion of asteroids onto detecting the transit of exoplanets?
Well, that's a good question. Of course, you'd want to use much longer integrations because your transits are probably going to last hours or many, many minutes at least. These events that we usually go after, a second or two is long. Very rare that you get one that lasts as long as a minute. I mean, almost unheard of. But yeah, so that has the advantage then that you would minimize readout noise because you can do in-camera integrations. Now, having said that, the Wattec camera can only integrate up to 4 seconds. And that's going to give you a pretty bright sky as well. That's a good question. If you're looking at a bright star, what kind of signal to noise do you get if you just over? Well, there's another problem, okay? These are 8-bit A to D converters, and so it's pretty easy to saturate. If you're trying to look at a bright star, you'd saturate it inside a tiny fraction of a second. But you'd also have one hell of a lot of points, which helps your statistics even if it, like that eunomia occultation that we looked at back here, somewhere. I don't know where it is. Anyway, that was a very bright star. I probably passed over it. Anyway, it was a very bright star, very bright asteroid, but it only dropped a little bit. But you could just tell by eye, oh yeah, there's an occultation there. Even though the width of the noise overlapped quite a bit. But there was so many points that it found the event with, super high confidence and accuracy. And that's probably what you would look for exoplanet.
The main difference is the time scale is different. Occultation takes about less than a second.
Right.
Like transit of exoplanet might take minutes.
It would take a long time, and yeah, and you'd have to have a pretty big computer because you'd have many gigabytes of data. Because even when you take a long integration, so you can go up to 256x, 256 fields integrated into one output. So it waits 4 full seconds, 256 fields, or 128 frames before it finally says, okay, now I'm going to send this out. So you just get one readout noise point. But still, it's taking all those frames, and it's going to record all those frames on you're going to have one hell of a long file. But Kirk keeps telling me storage is cheap now, and I keep saying, well, I spent $100 and some odd for that 2 gigabyte drive. What are you saying? It's not that cheap. Terabyte. Did I say gigabyte? Yeah.
How do you get a fractional pixel? You're talking like 2.4 pixels.
Oh, well, that's the average over, it is true. You only count real solid pixels. Where was that? See, when you got 80 slides, you can't find this. Yeah. There. So it's only whole pixels that are counted, but yeah, the radius is on average 2.4. Not on this one. This one's bigger than that, but yeah. So maybe the last thing I want to tell you is that it turns out, I didn't really know this until almost before I left. There's a really nice occultation tonight, half an hour ago. 9th magnitude star occulted by Lavorsky, actually a named asteroid. The shadow for it, though, went right across the spine of the Santa Cruz Mountains. So you can't see it from here. Otherwise, I'd have thought, gee, I wonder if we could get people interested enough to go out and actually watch me do one of these from here. But can't see it from here. Can't see it from Santa Cruz either. You have to go up to the top of the Santa Cruz Mountains. And we do have one of our team who lives there. So I did go through the process of making a planning page for it, and I hope that, and he said he was going to try it, so we'll find out. whether he got it. In fact, Kurt might even be able to do that on his phone. Did Carl get it or not? Of course, you're actually doing hard work here too, so yeah. Yeah. Well, the event was at 8:52, I think. It's 9:35. No email. Okay. So, anybody interested, maybe, in trying to take their interest to another rung higher? Maybe think about it.
Related question.
Yeah.
How does your Wattec camera compare to like these Astro cameras from ZWO or other vendors with this?
Well, those ZWO cameras have way more pixels,
Yeah.
and
Is it sensitive enough for this? You get like a planetary camera.
there's some debate. I keep trying, because I have a little bit of money left, and I gotta like spend it like really soon. I'm thinking, should I buy an Asteroid system, or maybe I should buy a ZWO 174 GPS,
Yeah.
or QHY 174 GPS. And I can't get a firm, like, oh my God, those are like way more sensitive than the Wattecs. I don't really care about pretty pictures that much. We've already got a camera and set up for that.
Yeah.
Um,
But a bunch of us are imagers and have those cameras.
already have them,
Would
yeah.
it be appropriate for doing this stuff?
Yeah. In that case, you're strictly digital, and in that case, what you would do is you would hook up a StarTech cable between your digital camera and your computer, and you download straight into the computer. You don't go through a camcorder, mini DV, or anything like that. Yeah, that's possible, and the IOTA site has people who are starting to do that. Okay, well, that's all I got.
Well, thank you.
Yeah, you're welcome.